Good evening, everyone, to this series of lectures that the INO project has been organizing for now about 32 weeks. And in fact, this is the 61st lecture in this series. And today it is a fantastic privilege for all of us to listen to Professor Rohini Godbole from Indian Institute of Science, Bengaluru. I'm 100% sure that none of us on the screen really requires, as of today, her introduction. But since these lectures are also recorded and available on the YouTube, it's also my pleasure to say a couple of words before I formally invite Professor Rohini to give her lecture. The title of the talk, of course, is The Legacy of Emmy Noether, which is not only the story of fantastic mathematics and real linkage to physics, but also a highly inspirational story of an individual. Um, Now, coming to Professor Rohini, our speaker, she did her PhD from State University of New York at Stony Brook, and she was also awarded DLIT by SNDT Women University of Mumbai. She held visiting positions at many international organizations. Some of them include Abdus Salam Institute of Center of Theoretical Physics, University of Dartmouth, CERN, DESY, University of Utrecht, and University of Amsterdam, and to just mention a few. Of course, she published more than 300 research publications, besides several monographs and textbooks, which are very popular. She is an elected fellow of all three Indian science academies, as well as the World Academy of Science. She has been chief editor of Pramana. She is known all over also for her active role in organizing and Pramana and maintaining all the standards of its publications, which is the Indian Journal of Physics, for many years from 2008 to 2016. Course, she has been awarded Padma Shri, the civilian award of Indian government, and also won the Distinguished Alumnus Award of IIT Bombay, SN Bose Medal, Meghnad Saha Award, JC Bose Fellowship, and RD Birla Award, and so on and so forth. So she co-edited two very popular books, Leelavati's Daughters, Women Scientists of India, and A Girl's Guide to Life in Science. She has been the chair of INSA and IAS panels for women in science. So over to Professor Rohini Godbole for her talk today on Legacy of Emmy Noether.
Thank you very much, Satya, for this very kind introduction. It's always a great pleasure to be talking in any conference that Satya organizes. So I have taken the liberty, after giving the title to him, change it slightly, though it is indeed, I'm going to talk about legacy of Emmy Noether, but in specific, I will talk about her life, her mathematics, and then I will talk about her theorem. So the title I have given now is Emmy Noether and her theorem. So let me see if what's happening. Okay. So this is, of course, as everybody knows, I'm giving this talk in lectures that are being organized in the INO series. So I should say that, as we will see, the work of Emmy Noether has had extremely close links with even the proposal of the neutrino, which the Indian Neutrino Observatory INO is hoping to study. So to begin with, who was Emmy Noether? Emmy Noether was a brilliant mathematician, and she lived from the late 19th century to early 20th century. And she is a woman who made the world of mathematics her own and left an indelible mark on it. In fact, she was the only woman included in a Hall of Fame exhibition held in New York. I forget exactly when, but it was called Men of 20th Century Mathematics. And Emmy Noether was therefore included in this particular exhibition. Very famous physicists and mathematicians, Pavel Alexandrov, Albert Einstein, whose name we all know, then Hermann Weyl, Robert Wiener. The ones names I have written in red are the ones that many of us, my physicist friends, will recognize. And they all described her as the most important woman in the history of mathematics. In fact, as I will quote later, Albert Einstein called her the mathematical genius. And what was her theorem? So I will give sort of a poor man's version of that theorem. And what she really was able to show that conservation laws of nature, and particular example is energy and momentum conservation, they are due to symmetrical nature features of nature. That is, for example, the energy and momentum conservation is because of an absence of any special point in space and time. That is the reason why the energy and momentum is conserved. That is, given the nature of space and time the way it is, these conservation laws are not optional, but they are inevitable. And as we will see later, the very postulate of neutrinos, which the INO is supposed to be exploring, it actually came due to this conservation law of energy as well as angular momentum. I like this picture very much, which I've taken from scientificwomen.net, and which really shows she lived from the late. Excuse me, I will be talking about when she lived exactly. I will give the exact years, okay? So just wait for a minute. So she passed away, if you want to know, in 1933, 35. So that's early 20th century and late 19th century. So she showed this bridge between symmetries and conservation laws, which is what I said Noether's theorem was all about. So this is a very sort of, one slide description of Emmy Noether and her different steps in her life as in her professional life. She finished her dissertation at University of Erlangen in 1907 in mathematics. In 1915 to 1933, as I will describe later, she was at University of Göttingen, and where she was invited by David Hilbert and Felix Klein. Then she was on, I think that was really one of the big honors she had, in my opinion, that she gave a plenary address in the International Congress of Mathematicians in 1932. And believe it or not, but she didn't have a permanent job even at that time. She moved to the US Bryn Mawr College in Pennsylvania in 1933, and unfortunately left this world rather early in her life in 1935. The three things that I have written here, number fields, calculus of variations, and non-commutative algebras, are the three different fields of the important, which describe her different branches of mathematics that she worked on. In fact, calculus of variation, and that is the symmetry connection, was the subject she worked till about 1918. Then essentially the number fields and rings and ideals and so on and so forth, that work was done till about 1927, and the work after that was on non-commutative algebras. And what I have given here is, I will go back to this again, so you need not worry about it, but I have just reproduced the abstract of her paper, in which she proved two theorems which go by the name, generally are called Noether's theorem, but they are really Noether's theorems. She proved two separate theorems, and the title is Invariant Variational Problems. So and as I said, the layman's or the physicist description of these theorems is indeed here, that she worked out how the symmetries and the conservation laws are intrinsically linked, and the calculus of variation or the variational methods is what really she used to explore this connection. So that's what she says here. What follows thus depends upon a combination of the methods of the formal calculus of variation and of Lee's theory of groups. So this is really the essence of the two theorems of Emmy Noether, which sort of, according to me, have changed the world. Theoretical physicists began to look at laws of nature. So how will I do this talk? I will first talk about Emmy Noether and her world line. Then I will describe to some extent the relationship between the conservation laws and symmetries of nature. And here I will do a little bit of a formal description of this connection in the context of mechanical laws, mechanical symmetries. And then I will very briefly talk about the role that these theorems played in the development of theoretical descriptions of particles and interactions among them. And then I will like to summarize what I think is a legacy of Emmy Noether. In fact, this part written in blue is her legacy for physicists. I am not equipped to talk about her legacy for mathematicians, but I will only quote other people who talk about her legacy for mathematics. And then I want to talk about legacy of Emmy Noether as a woman theoretical physicist and mathematician. So let's see how this goes. So she was born in 1882, rather close to the end of 19th century, and in a Jewish family, which has implications later on. Her father was a professor of mathematics at University of Erlangen. And during that period, when she wanted to study at the university, women were only allowed to audit lectures. Mixed gender classes were not considered good. So therefore, she audited lectures with the permission of professors. And by the time she decided that she wanted to do a dissertation in mathematics, actually the universities allowed women to register to do PhD. So in 1907, she finished a dissertation on theory of invariants. As you might have noticed, the title of this paper was also about invariant variational problems. And as we will see later, it is because of her experience with invariants that Hilbert and very famous mathematical physicist and Einstein, whose name we all know, actually turned to Emmy Noether to ask her to help them understand some problems they were facing in understanding implications of some equations of general theory of relativity. But anyway, that is a little bit later. So 1907 to 1915, when she had finished her dissertation, she actually stayed in Erlangen working on mathematics. And this was not a paid position. And her father, and I think her brother, was also an academician. And they supported her doing mathematics in this period of about 7 years. In 1915 or so, she was invited to Göttingen, and which at that time was the center of creative science in Germany. And mathematical physicists David Hilbert and Felix Klein invited her there. For those of you who are on the, at least I'm hoping that there are students who are listening to this. So I should say that Hilbert is the same Hilbert of Hilbert spaces, which we talk about in quantum mechanics. And the Klein is of Klein bottles, which we come across in topology as a curiosity, even if we are physicists. So in fact, as I already mentioned, Hilbert and Einstein needed her help or asked her to help to understand the apparent non-conservation of energy that they noticed in that the equations of general theory of relativity implied. I'm not going to talk about in detail about that, but because that makes me too technical. But nonetheless, her sort of she started looking at this problem because of the questions they asked her. And she actually solved their problem by formulating the two theorems, what I call Noether's theorem 1 and Noether's theorem 2. I think actually the theorem she proved in 1916, because or 17, that is when we celebrated 100 years of Noether's theorem, but it had to be communicated to the Gesellschaft, which is the counterpart of the academy there at that time in Germany, Science Academy. And since she was not a member of the Gesellschaft, she couldn't act because she was not, she had not habilitated, as it is called. And therefore, the paper was presented in 1918 by Felix Klein to the Gesellschaft. So you will notice this here. I just want to show you this here, invariant variational problems for Felix Klein. She had written it for Felix Klein on the occasion of the 50th anniversary of his doctorate. And it was presented by Felix Klein in the session of the Gesellschaft on 26 July 1918. But as I said, she had done the work a little bit before. And in fact, for the first 4 years in University of Göttingen, she could not teach on her own because in those periods of at that time in Germany, you had to do an habilitation, and the university had to allow you to do habilitation to be able to teach. And some of the philosophical faculty at the university felt that the brave boy is coming back from the war will feel very strange learning from a woman. So they opposed for about 4 years. And in these 4 years, David Hilbert was extremely supportive of her. So he announced lectures in his own name, and which Emmy Noether was giving those lectures, because as per the tradition of that time, one actually got paid by the students who took your lectures. So this was still even after 11, so roughly 11 years after for 11 years after she finished her dissertation, she had no paid position till till about 1919, by which time the university finally relented, and then she was allowed to present her habilitation. And from 1919 to 1933, she spent her time at University of Göttingen, and there she developed the fields of Noetherian rings and non-commutative algebra, and made very fundamental contributions to mathematics, which I wouldn't even be able to summarize. They are sort of really beyond me. In 1932, she gave this plenary address in the International Congress of Mathematicians, and as far as I know, she was the first woman recipient of the Ackermann-Teubner Prize. And this is a very famous photograph before she, I think, left for the US. And this is Emmy Noether here with all the students flanking her, and also some women among them, which was nice. So they were called all Noether boys. And from all the records, it is clear that she was extremely generous with her comments and her ideas, and was a very impressive and influential mentor or teacher. Many of her students went on to become leading mathematicians of 20th century. And as I already said, she started new branches of mathematics. So 1933, due to her religion and the political environment, she had to move to the USA, and she could not find a position at a big university at that time. To me, this is already a sad commentary, but at the same time, this is also a sort of an interesting part that you can notice, that the person who actually made a lot of efforts, and actually she went to Germany to meet her, and this is a mathematician herself, Mary Agnes Scott, who had moved from Great Britain to USA, and she was the head of the department. I'm not sure whether she was the head of the department of mathematics. She was a mathematician for sure. And there is a famous women's college called Bryn Mawr College in Pennsylvania. And she raised money to be able to offer a position to Emmy Noether at this college. And from this college, Emmy Noether traveled twice a week to Princeton University to give lectures on differential geometry, which Albert Einstein used to attend. And at least she goes on record for saying that she really did not like professors at Princeton's. She did not find the same congenial scientific atmosphere as she had seen in Göttingen. And unfortunately, in 1933, 35, sorry, this is a typo. In 1935, she passed away due to health complications after a surgery, which unfortunately nobody knows exactly what went wrong. So this is the lifeline of Emmy Noether. And from her obituary in New York Times, I have reproduced some lines, because I think that these few lines describe both Emmy Noether, her life, and her mathematics most evocatively. So he said that in the judgment of the most competent living mathematicians, I already gave you a few names. Fraulein, that is a German in Einstein, because she was Miss. So it's not Frau, it's Fraulein. Fraulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. In the realm of algebra, in which the most gifted mathematicians have been busy for centuries, now this is an area which was very, people have been working for a long time. And here she made some very original contributions by discovering methods which have proved of enormous importance in the development of the present day younger generation of mathematicians. So she charted new paths in a subject which has been had a lot of activity for centuries. Pure mathematics, he goes on to say, is in its way the poetry of logical ideas. And I think to some extent it goes also for theoretical physics. One seeks the most general ideas of operation which will bring together in simple, logically unified form the largest possible number of formal relationships. In this effort toward logical beauty, spiritual formulas are discovered necessary for the deeper penetration into the laws of nature. And in these last few blue lines, in some extent, some way, describe Emmy Noether's work that is reflected in Emmy Noether's theorems. Then he goes on to say, born in a Jewish family, distinguished for the love of learning. I'm pointing these things out because that tells us what helped Emmy Noether to be what she was. And that is because she began her life in a family which was distinguished for the love of learning. It is the same, the parents, the brother who, after she finished her desert, first they supported her to have the degree. After the dissertation, when she didn't have a job, they supported her for 7 long years. So Emmy Noether, who in spite of the efforts of the great Göttingen mathematician, Hilbert, never reached the academic standing due her in her own country, nonetheless surrounded herself with a group of students and investigators in Göttingen who have already become distinguished as teachers and investigators. These were the Noether boys and the girls whose photograph I showed you. I could in fact list them, but since none of us are pure mathematicians, those names won't mean much to us. But what I was pleased to see of that, there were men as well as women in her among her students who did some fundamentally important mathematics in her wake. Her unselfish, significant work over a period of many years was rewarded by the new rulers of Germany with a dismissal, which cost her the means of maintaining her simple life and the opportunity to carry on her mathematical studies. This is what she suffered because of the religion that she had, as she was born in a Jewish family. And then he goes that far-sighted friends like Mary Agnes Scott, and they are friends of science is what he calls them. In this country, were fortunately able to make such arrangements at Bryn Mawr College and at Princeton that she found in America to the day of her death not only colleagues who esteemed her friendship, but grateful pupils. And I think that was actually really an important point in Emmy Noether's life, that she always had pupils. She was surrounded by pupils who loved her and who sort of hang to every word that she uttered, and they learned enormously from her. And it was her enthusiasm that made her last year the happiest of her entire career. This is Albert Einstein in New York Times, May 1st, 1935. Now, I think this kind of summarizes the greatness of Emmy Noether as a physicist, as a mathematician, and she did such fundamental contributions to theoretical physics that I keep on thinking of her as a physicist. But it also talked about the tribulations that this brilliant mathematician had to actually suffer. So I particularly like this obituary extremely well. So now, having said this, I have now sort of come to the first part of my talk, namely Emmy Noether. And I will now want to go over to the talk about her theorems. So when I want to start talk about her theorems, I want to step back a little bit. And I want to tell you about words that I would need to use. One of them is the conservation laws. Okay. Now, in the development of particle physics, the symmetries of laws of nature have been really be the underpinning in the entire development. And Noether's theorem, which revealed the great connection between the continuous symmetries and the conservation laws, have actually been therefore responsible for the development of particle physics. And these symmetries could either be simple space-time symmetry transformations or some internal symmetries. In the coming slides, I will try to explain what is meant by these symmetries. But before I do that, let me just say what were the impacts of the two Noether theorem. The first Noether's theorem, actually, as I already said, provided an understanding of the space-time symmetries of the laws of nature and its implications. And there it was able to show that the conservation laws, there are certain conservation laws which are sacrosanct and which have to be satisfied independent of the details of the dynamics of the interaction among particles. And the example of that was the energy conservation. So it actually removed the mystery in which energy conservation was shrouded for quite some time in particle physics, and so much so that later on the energy conservation was actually used for postulating new particles, and not just new particles, even new interactions. Now, the second theorem was actually which provided deep understanding of the observed features of some particular dynamics. And the example there, again, I will, once I've talked about it, I will go back to this. And this is to do with Hilbert's improper local conservation in general theory of relativity. This is the apparent non-conservation of energy that was a bit of a problem. And this was then understood in terms of the relationship between invariances and conservation. So what is important to tell you here is that her result was completely general. She was not proving this theorem for us particle physicists. It's just that we particle physicists have been finding more and more special cases of a theorem, and her theorem has guided us to finally today, the ideas of symmetries and conservation have really guided us to arrive today at the description of particle physics as we see it. And for example, this is Einstein's comment on her first paper, on the paper which I displayed to you. He says, yesterday I received from Miss Noether a very interesting paper on invariant forms. I'm impressed that one can comprehend these matters in so general a viewpoint. What I meant to say is that they had asked her to address or understand, help them understand this particular problem which was present in general theory of relativity. And what she did was that, like a typical mathematician, she proved a general theorem which could be applied to many different things. So first, what are symmetries? As if a system remains unchanged by a particular operation, we call that operation symmetry of the system. What kind of operations can be there? For example, a translation of origin of space and time through a fixed distance. So if we are describing a body, instead of describing its coordinate with respect to our origin at, let's say, at this point, which my pointer is indicating, instead of that, if I shift the origin of my coordinate system to this second point where my pointer now rests, nothing will change in terms of the description of that system, and that is the symmetry of the system. On the other hand, you can do rotation of coordinate axis through some fixed number of angles and continuous rotations, and sometimes you could flip a system by reflect it in a mirror and it will still remain the same. Different kinds of symmetries, operations will correspond to different symmetries. Now, there are discrete symmetries. For example, reflection in a mirror is a discrete symmetry, whereas this translation of origin of space and time or rotation of coordinates can actually be continuous symmetries. And continuous symmetry is a symmetry where the transformation property can be parameter can be continuously varied, and therefore any particular element of transformation can be brought about from identity, that is no transformation at all. For example, a translation through a finite distance A can be thought of as a series of n very small translations, each through a distance delta A equal to by n. This should be distance and not angle. And a rotation through a finite angle theta can be thought upon as a series of n infinitesimal rotations through angle delta theta, such that total theta divided by n is delta theta. And what Emmy Noether did, or her theorem did, it talked about the effect of such systems which might have such continuous symmetry transformations. Okay. So now what you want to do is that you want to talk about behavior, important thing that you want to do is, one thing you can do is you can look at the symmetry operations of just a system. So I can take a cube and I can say that if I rotate that cube through 90 degrees, the cube will look the same. That is one kind of set of symmetry operations. But now you can ask a question, not just of a body, or a system. You can ask a question of equations of motion. And you can ask the question, how do the equations of motion change under these transformations? And clearly the physical laws that we know, for example, Newton's law of motion, has been extracted from a large amount of data on time evolution of physical systems from a set of initial conditions. And these are indeed the laws of physics. And since we could extract these laws, that actually tells us that the laws of equations of motion are actually independent of the choice of origin of space and time, as well as the choice of rotation of coordinates through some angles. So they are clearly true properties of the laws of equation of motion under certain, for example, for a free body. And therefore, this is something that you can see that there are symmetry operations. These are the symmetry operations. And one can also see what is the, if then there are continuous symmetry operations. And then you can ask the question, what is the effect of these symmetry operations on equation of motion? So let me just look at this particular thing. Let me just look at how the laws of physics will look when you change the choice of origin of space and time, or you change the orientation of coordinate axis. So here, what we have to, so what does this mean? We know that space by itself does not distinguish any one point as special, and time, any specific time also cannot be very special, because if I do, for example, a pendulum experiment today, or somebody else did the pendulum experiment 150 years ago, or somebody will do it 150 years from now, the result that you will get of the motion of the pendulum will remain exactly the same, no matter where you perform the measurement, whether you perform the measurement in US, or whether you perform it here, or you perform it in Australia, where we are, at the other end of the earth. So clearly, and when you make those measurements, then you will extract the law of motion of pendulum. So the law of motion of a pendulum, for example, is not dependent, cannot be dependent on the place where you perform the experiment or the time. What I mean by this, obviously, is that there are equivalent places I have to find. Obviously, if I find a place where there are some obvious, there is some space which has a different region of space, which has some additional forces acting on it, clearly the equations of motion will be different. So I'm talking about identical experiment, identical spaces, but separated from each other by space and time, and the laws of motion that we will find will be the same. So let us look at Newton's second law of motion, and that is in terms of coordinates x, y, z. One can write it like this: m d2x by dt square is equal to the force, x component of the force. M d2y by dt squared is equal to f y component of the force, and m d2z by dt square is the z component of the force. Or equivalently, I could write a vector equation: m d2r by dt squared is equal to vector f. Now, where r vector is simply the x times unit vector along the x direction plus y times the unit vector along the y direction plus z times the unit vector along the z direction. So these are the Newton's laws of motion. And while looking at this, it's clear to us that if we make a transformation and we say that instead of measuring time from origin of time at a point t0, if we change it to some other new point t0 prime, as you know, dt square will not change if I shift my origin of time by a constant amount. Similarly, this will also not change if I shift the origin of space by a fixed amount, nor will, therefore this equation will completely remain unchanged, and hence we see that these laws of this particular equation, as we see, is the form of the equation does not depend on the space or time or orientation of the coordinate axis. So what does it mean for physics? So I want to just give you an example. What is meant by rotational invariance? Here I have shown you, for example, Earth going around the sun. And if I have a choice of coordinate axis, which is tilted with respect to this choice of coordinate axis, then the orbit that I will see will also be tilted, obviously, under a rotation. So the implication of rotation invariance is not that all orbits are necessarily circular. But what the implication of rotation invariance is that the relative orientation of the sun and the earth will be the same no matter what is the orientation of the observer's coordinate axis. So this is a symmetry, and this is a depiction of the symmetries of laws of motion. Actually, along with the symmetries of the laws of motion, we also knew about conservation of various mechanical kinematical quantities. For example, we knew that from Newton's first law, we know this, that a linear momentum is conserved in the absence of force, or in the absence of a torque, angular momentum is conserved, and total energy of the system in motion is also conserved, and that is where we have conversion of potential energy into kinetic energy, or vice versa. When we understand how a pendulum works, we always understand that at this extreme position, the pendulum has only potential energy. At this time, when it comes to this central position, it has only kinetic energy. And again, when it goes up, it has only potential energy. It comes to rest, and then it starts swinging back again because there is an attractive force. Again, it starts swinging back here after coming to rest. So this is the conservation of energy that we see, and we derive actually the various quantities related to pendulum motion using this conservation of energy. This is, of course, the conservation of angular momentum. As a dancer, which is who is pirouetting, has to, when she starts going faster and faster, she has to close her hands. So this is where one says that the angular momentum is conserved in the absence of a torque. But these were only observations. One did not know the reasons why. And Emmy Noether's theorem actually proved that for every symmetry operation generated by a continuous transformation, there was a conserved quantity, and there was a continuous symmetry, which we will discuss to some extent, translation in space, and the corresponding conserved quantity is the linear momentum. There is a rotational symmetry, which tells you that the angular momentum is conserved. Translation in time implies that energy is conserved. So there is a relationship between a symmetry transformation and a conserved quantity. And in the technical words, which I will not go into, the conserved quantities are nothing but the generators of this continuous symmetry transformation. So this is the essence of our first theorem. And let me see how I can talk a little bit more. So again, I have said the same thing that I said in the earlier slides, but along with these various mechanical quantities, kinematical quantities, such as momentum, energy, and angular momentum, physicists had also noticed that, for example, things like electromagnetic charges are conserved. And what Emmy Noether's work did that paved the way to show that all the observed conservation laws are related to symmetries that either the space-time itself exhibits or some of the equations of motions exhibit, and some internal unknown observables. I will come to this internal symmetry a little bit later. Let me first discuss only the context of mechanics. So to discuss the theorem by itself, let me see, I have 15 minutes. So let me just first introduce some notations. If you remember, I wrote the Newton's laws of motion by using coordinates x, y, z. But we need not use x, y, z. Sometimes it's easier to denote, for example, coordinates r, theta, phi, where x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, and z is equal to r cosine theta. So instead of calling my coordinates strictly x, y, z, I will call them q. Okay, so that is my general notation for a coordinate q, which specifies the position of the body at a given time, etc. Now, Newton's law, 3 laws of motion actually tell us how, with initial conditions and the forces acting on the system, how will the particles, the body move under the action of the forces under it. And that's what Newton's 3 laws of motions are all about. Now, what you can of course try, you keep only using Newton's laws of motion, and you can write down all the forces that are acting on a particle and work out in detail the dynamics of the mechanics of the motion of the particle. But there was a very famous mathematician, physicist called Lagrange. He showed that the equations of motion can also be derived by using a function which we call Lagrangian. And this Lagrangian is a function of the coordinates of the system and time. And that is the sum of 2 quantities, rather the difference of 2 quantities. One quantity is the kinetic energy and the other quantity is the potential energy. So, for example, we know that the kinetic energy of a free particle will be p square by 2m or half mv square. And that is this half mq dot square, because v is dx drr by dt. I have written it as dq by dt. And v will be 0. So Lagrangian, for example, for a free particle will be simply p square by 2m or half mq dot square. If a particle has a force acting on it, then this potential and has a potential energy as a result of that, that potential energy will also appear in the Lagrangian. And now equations of motion follow from this Lagrangian function by using a principle called principle of least action. You have to bear with me for some details, I think, to do justice to sort of see the generality of this theory. I want to give you some details which are mathematical. So mechanics is then described by this function Lagrangian, which is a function, as you can see, sorry, it should have been q and q dot. I made a mistake. It's a function of q, q dot and time. And that's what it is, L, q, qt, q dot and t time. And this is a function of the generalized coordinate qt, its time derivative q dot t and time t. In all generality, Lagrangian is a function of all these 3 things. And then the equations of motion can be obtained by minimizing a quantity, which is an integral, and this integral is called action. And this is an integral of this Lagrangian over a path going from time t equal to t naught to t equal to t1. And solutions of the equation of motion would mean that we want to find out q as a function of time, and the q as a function of time, the equations that are satisfied by q as a function of time is the equation of motion, and which will be given by minimize. I will explain the next slide how you minimize the action. But from this Lagrangian, the equations then follow, saying that dl by dq of t minus dt dl by dq dot t equal to 0. Since I talked about a free particle, let me just show you that for a free particle, the equation of motion should be 1/2 m v square should be equal to either it should 1/2 mv square, that is 1/2 m d2x by dt square should be 0. If that is 0, then the particle will remain at rest, if it was at rest, or it will continue in state of uniform motion. That means dq by dt would be finite, but d2q by dt square will be 0. So let us just see if this equation follows. Indeed, if LQQ dot t is simply half q dot square, then you can check for yourselves by doing this that the Lagrangian is independent of q of t, because it is only half q dot square, and then half mq dot square. And then if you do dt dl by dq dot t, the equation you will get is d2q double dot by dt square is 0, which is exactly the equation of motion for a free particle. So I've shown you that this Lagrangian and equations of motion that we get from this Lagrangian indeed match with what we know from Newton's laws of motion. Now the question is, how do I derive this from here? And that is something that is done, and this was done by Lagrange, and this is called Euler-Lagrange equations. What you do here is that you look at this quantity action, and then you say that I want to find out the path that the object takes from time t0 to t1, where what is the function of q of t, that the equation that q of t should satisfy. Now what I do is that what one does is that one looks at a slight variation of the path in the coordinate space, and one says that let us look at q of t, q prime of t, which is equal to q2 plus delta qt, again between times t0 and t1, such that the motion starts at the same place and ends at the same place. Therefore, q prime of t0 is q of t0, q prime of t1 is q of t1, because it is at two fixed points in the coordinate space. And then you ask the question, what is this integral? And you say that you demand that the integral be actually an extremum. I have written it as a minimum, and that is variation in this integral be 0, and that q which you obtain, which is really obtained in reality, is the one which minimizes or extremizes this action. And this is a bit like Fermat's least time principle in optics, which says that the path taken by a light ray in a medium is the path that takes the least time. Instead of the least time, we are going to say that the path taken by a body from time t0 to t1, that it follows from time t0 to t1, is the one which minimizes or extremizes this particular quantity. So if you do the algebra, you actually find that this is indeed the equation of motion. Now, what you want to do, you want to say that, okay, given a Lagrangian, I can find out an action, then I can do a variation of action, and I will find these equations of motion. Now, the question that you want to ask is the next step, that if I consider a transformation of these coordinates from the observer's point of view, like I talked about, namely changing the origin of time. I'm going to do that in a few slides. So supposing you do any symmetry operation like that, or you change the orientation of the coordinate axis. So if you do such operations which leave equations of motion invariant, what is the effect of these symmetries on the Lagrangian itself? Because we have just said that the equations of motion are going to remain unchanged, but under what conditions? What is the effect of the symmetry operations that will leave the equation of motions unchanged, is the question that you have to ask, because you want to find out the sort of effect of these symmetry operations on the equations of motion. And so there, and this actually, when you can look at this and you realize that since the equations of motion are obtained by extremization of this quantity, the total change in action should be 0. And this means that under symmetry operation, L can at most change by a total time derivative, so that the change in action is 0, because action is nothing but the integral of this. And if the total change in L is a total time derivative, since you are taking the action between two fixed points, and these are like the two end terms, the net change in the action will be 0. So that's exactly the point. And this is something similar. This is really what, very rough way, what Noether's theorem dealt with in all its generality. So let me just try to see if I can apply the arguments of her theorem to the above mentioned case of the mechanical ideas. And again, I have reproduced the first slide abstract of a paper, and remember now that I am going to look at what she says is that you use the methods of the calculus of variation. So I'm going to use the methods of calculus of variation. So let me consider a symmetry transformation that where q prime of t that is q of t is changed to q prime of t under some symmetry transformation. For example, q prime of t is equal to qt plus delta s qt. And since it's an infinitesimal transformation, I would sort of change this total change delta s. I will split into two parts. So number epsilon, which is small, and a capital delta, which can be a principal function of qt, q dot t, and t. Now, the example of symmetry operations that I will look at particularly, for example, is t prime. Change the time t prime to t plus epsilon. In that case, delta of Q of T will be simply Q dot. Okay. On the other hand, when I say that I change x prime to x plus epsilon, then the delta Q of T will be 1 because it will be the coefficient of this epsilon. Now, if this transformation is the symmetry of the equation of motions, then we just now argued that it means that under this transformation, the Lagrangian can change only up to a time derivative. So I can do now some little bit of variational algebra. So the variation of the Lagrangian under the symmetry transformation is nothing but the Lagrangian in terms of Q prime, Q dot prime and T minus the Lagrangian in terms of Q of T, Q dot T and T. This you can do the little bit of an algebra, and using equations of motion, you can show that it reduces to total derivative of dl by dq dot times delta sq of t. So the change in Lagrangian or the variation of the Lagrangian is indeed this. But remember, this delta sq of t I had written as epsilon times capital delta. So this becomes d by d, the left hand side here becomes epsilon d by dt lambda qt q dot dt. And therefore, now what we see is that if I take these two equations, I can see that d by dt of this quantity in the square bracket is 0. And this tells me that d by dt of this particular quantity q of t is 0. Now, depending on my Lagrangian, depending on my symmetry operation will tell me what this capital delta is. My symmetry operation will tell me what dl by dt is. The change delta SL will tell me what capital lambda is. And now the charge Q of T, you find a very interesting property. D by dt of Q of T is 0. What does this mean? That means that even if I wrote here T, this Q is independent of time. So that is a conserved quantity if this symmetry transformation Q prime T equal to Q of T plus delta S QT has a symmetry operation. So if the change in the coordinate are due to the symmetry transformation is given by small delta S Q of T, we find that for this symmetry operation to be if this symmetry operation is a symmetry of the equations of motion, then a quantity which I obtain from the Lagrangian in this formula will actually be a conserved quantity. So this is the essence of Noether's theorem. So therefore, d by dt of q of t is 0. That means q of t is the same at all times. Let me call it q naught. So this is actually in some language, some paraphrasing of first theorem of Noether. And she actually then says that q naught is the conserved charge, or what is known as the first integral, which is known to mechanics, which is what she mentions in her paper. So now let me specialize to the case where L has no time dependence, explicit time dependence. I can have a system like that. And let me consider the operation of simple time translation. Now, since the choice of origin of time cannot affect the equation of motion, it is clearly the symmetry of the equation of motion. And equation of motion, solution of equation of motion gives me the trajectory q of t as a function of time. Therefore, q prime of t prime must be equal to q of t. So therefore, delta qst is nothing but q prime t minus q of t, and t prime is t plus epsilon. So I get rather minus epsilon, and that will give me minus epsilon q dot. Now, if I do a very, very similar calculation that I did here, okay, I can show you that q naught in this case will simply become p of t, that is dl by dq dot t minus lqt q dot t. Now you can write down for a free particle what is dl by dq dot, because m half q dot square is the Lagrangian, and then you will find that the charge q0 is nothing but momentum p times q dot t minus lq dot q dot t. And this is the momentum which is conjugate to that particular coordinate. And this right hand side is nothing but the Hamiltonian of the system, and is nothing but h equal to t plus v. So if you can start with the L equal to t minus v, and you look at the symmetry operation under the transformation t prime equal to t minus epsilon, and this actually tells you that symmetry of the equation of motion under time translation implies that the Hamiltonian is the conserved charge. This is the Hamiltonian, and Hamiltonian represents the total energy. Hence, Hamiltonian conservation means that in mechanical systems, the energy is conserved. So just you see that this conservation is now follows just from the mechanical description that any equation of motion should be independent of the choice of origin of time. So in fact, energy conservation was very well known, as I already said, and it was known in all the held to be true in all theories, except for some problems in general theory of relativity. But to quote Feza Gurse from an article by Nina Bayer, before Noether's theorem, the principle of conservation of energy was shrouded in mystery. We didn't know whether there was any fundamental reason for the energy to be conserved. And Noether's simple and profound mathematical formulation did much to demystify the physics and told us that energy and momentum are conserved simply because the law's description of physics, description of phenomena does not depend on a spatial point in space or time. So her theorems therefore said that for all theories which have finite continuous symmetry group, energy conservation was non-negotiable. So did physicists know of any place where energy was not conserved? I already, one of the important things which many of us have heard, and this is the connection with neutrinos, that Chadwick actually in 1918 had seen the beta decay. All of us learned the beta decay in nuclear physics course. And this is this famous beta decay where bismuth 210 goes to bismuth polonium 210 and an electron is emitted. And what one found that the energy spectrum of the electron from the 210 bismuth was continuous, and only here near the end point did the energy of the electron in MeV matched with the difference in the energy Q value of the energy when the between the 210 bismuth and 210 polonium transition. But otherwise there was an apparent non-conservation of energy, and physicists were actually quite desperate. Bohr was even making proposal that energy conservation is violated. Remember, Noether had proved that theorem and its inverse already in 1918, but 1617 actually. And she had shown that if energy is not conserved, then theories are not invariant under time translation. And therefore, people were really worried that what's happening if there is deviation, why are we seeing an apparent violation of energy? And Pauli then postulated neutrino production in the radioactive decay to preserve not just the conservation of energy, but I cannot go right now into the details, but it also conservation of, there was also an apparent non-conservation of angular momentum. Then he also wanted to preserve exclusion principle, which he had himself postulated. So because of these two things, he postulated it to be a spin half, that he said that along with the electron, a spin half neutral and almost massless particle, which he didn't say actually, the neutral and spin half particle is emitted along with the electron. That was his postulation, and that he himself declared was actually complete desperation to the radioactive ladies and gentlemen. He had written this letter. And now we know that the observed endpoint of the beta spectrum means that the mass should be very, very, very small, but this was not postulated by Pauli. Enrico Fermi in 1934 used this idea and gave a theory of beta decay, where he christened this particle as the small neutron. In Italian, anything with an O at the end becomes a small, so it was a neutrino. And indeed, he showed in this famous paper that the mass of the neutrino being zero was consistent with the observed energy distribution at that point, and indeed said that by measuring the shapes of the electron energy near the end point, that is, mind you, that is this spectrum, this spectrum, that by measuring the energies of the electron and the shape of the spectrum accurately near this endpoint, he said in this famous paper that you can actually determine the mass of the neutrino. And even today, there are some measurements of the mass of the neutrino which try to employ this method. So not just Noether's theorem sort of drove Pauli to postulate a new particle, which after many decades was found to be true. Her theorem at that time also removed an apparent contradiction in general relativity. As I said, Hilbert and Einstein were puzzled by the non-conservation of energy, and her theorem showed, and that is the second theorem, which I like to call, that there was nothing wrong with conservation of energy. One was missing the piece that was coming from the back reaction of the space-time curvature. And as I already told you, that Pauli used the idea to predict a new particle. So this is when, around the time when Noether had postulated, given her theorems. Actually, at the time of her theorem, one did not much think of non-space-time symmetries of laws of motion, but I can give you an example. And for example, the equation of motion under the action of electromagnetic fields. For example, one can change the origin from where electrostatic potential is measured without changing the expression for the force and an electron. As you remember, the force and electron, electrostatic force, is E times electric field, and the electric field simply depends on potential difference, and therefore the force depends only on potential difference, as a result of which you see that the origin, that if an electron is traveling between two plates, one at potential V1 and other at potential V2, you could say as long as V1 minus V2, it is the only V1 minus V2 that determines the energy of that the electron will get in falling from one plate to another. So if instead of calling this potential V1, I call it V1 plus 10, and I call the other potential V2 plus 10, nothing changes. And this simple observation actually can be shown later on to lead to conservation of electric charge. So what Emmy Noether's theorems had told us, that there must be a relationship between any conservation and there must be a corresponding symmetry associated with symmetry transformation associated with a conservation. So this example that I've given you about conservation of electric charge is the first example of an internal symmetry. It does not act on space-time coordinates. It does not say, let T prime go to, let me change the origin of my space and time. But here it says, let me change the origin from where I measure my potentials. So these intangible quantities such as potentials, either scalar potential or vector potentials. Now you think in terms of symmetry transformations and of these potentials. And this, now I'm going to take many ideas, many decades jump, and I'm going to say this particular symmetry is called the U1 gauge symmetry. And this point about the relationship between conservation and an internal symmetry actually drove the path of the evolution of particle physics. The general path of last, I don't know, actually 60, 70 is wrong. I should perhaps say more like almost now 80, 90 years. And what is it? You use the theorem and observed conservation laws. Then you extract symmetries of the equations of motion, from which you extract the symmetries of the dynamics. And I gave you one example, that is the U1 invariance of electromagnetic equations, interactions. And these, for example, the corresponding divergence equations. Because remember, the most important point of Noether's theorem, which is in the paper, given in the paper, and which oh God, sorry, I have lost, 1 second. And I don't know what's happening. I want to, yeah. Let me show you what I want to get at. Yeah. So this particular equation, that dqt by dt epsilon is equal to 0, this is what she calls, it's a special case of what she calls the divergence equations. And therefore, what we see is that any symmetry, okay, will give rise to a divergence equation, and those divergence equations in the case of gauge interactions are called wide identities. For example, this also led to the idea of what is called conserved vector charge in weak interactions. I'm giving these names just to tell you that all these ideas in particle physics essentially were arrived at through the connection between symmetries and conservation. For example, the invariances or symmetries and the well-being of theories such as renormalization, that gave to the idea of cancellation of anomalies, and even the particular particle spectrum that we see in particle physics today, now we understand is that with that particle spectrum alone, we find that the gauge theories can have some very nice properties. Then the generalization of this U1 symmetry to new theories was the electroweak unification. Then new theoretical ideas came about spontaneous symmetry breaking and the Higgs mechanism. And all this came from this basic understanding of relationship between the symmetry transformation and the invariances of law of motion. The technique theoretical shortcomings of the current theory actually has led us to postulate some new symmetries, for example, supersymmetry. So this is the story of particle physics since the days of Emmy Noether. Let me give you very briefly run through in 2-3 slides, for example, with the one story that all of us are familiar with, that about the Higgs boson. So I want to tell you what is the origin of the statement that Higgs boson gives masses to all the particles. What it really means is that the interaction of matter fermions with Higgs bosons make the existence of a non-zero mass, which is actually experimentally observed, consistent with different symmetries which one had extracted from the behavior of the laws of the fundamental forces. So by saying that this symmetry is a fundamental property that the theories must have, people actually postulated the existence of the Higgs boson. And what would have gone wrong if the theory didn't have these symmetries? If the theory didn't have these symmetries, the quantum formulation wouldn't have made sense. If the quantum formulation didn't make sense, then of course all bets were off. But the fact that this made sense was told to us by experiments which were performed in the Large Electron Collider in the 90s and at the Tevatron in the Fermi Laboratory, Chicago in 95. Therefore, the Large Hadron Collider was actually constructed and it did find the Higgs boson, then in fact confirming that our theories do indeed have the symmetries which we had extracted from the observed behavior of the laws of the fundamental forces. And that's when we said, aha, we have found the Higgs boson. It's quite something. So this is a very nice presentation that David Gross gave about connection between physical phenomena, symmetry principles, laws of nature. And I think this kind of exhibits to you the role, tells you clearly the role that Emmy Noether's theorems must have played in the development of the entire world of particle physics as we see it now. I have given you one example, and that was the postulate of the neutrino. Now, there are many ways of extending the standard model. There are some which are trying to include gravity in the description. And for example, one of them is the ones on which I had worked for a long time. Unfortunately, we haven't found any evidence of supersymmetry, but that's a new symmetry of nature that people have postulated for many, many decades. It also is sort of something that the world of particle physicists has been studying with a great interest. And right now, the standard model is actually like the equations of motion of all the observed particles can be actually written down in terms of a Lagrangian. I told you, equations of motion come from a Lagrangian, can be written in terms of a Lagrangian, which fits on the back of a t-shirt. But we don't think this is the whole story. And therefore, experimentalists and theorists alike are trying to make studies at the Large Hadron Collider. And maybe, the theory frontier is to see how to include gravity in all these description. And the story goes on. So you see that one cannot overemphasize Emmy Noether's contribution to particle physics. They have guided the development of our current understanding of particles and interaction among them at all steps. And that, in addition to that, the second legacy of Emmy Noether, of course, is not according to me. I mean, I really feel that just like every school child knows about Marie Curie, they should know about Emmy Noether. She even, grew a little bit before Marie Curie. And she was the first woman to get this Ackermann Teubner Memorial Prize. And it took, many, many decades, as you can see, till Mariam Mirzakhani became the first woman to get the Fields Medal. She is a source of inspiration to all the women theoretical physicists and mathematicians, where they are still somewhat small in number. I can tell you that when I was studying, I never knew that it was Emmy Noether. I knew Noether's theorem, like there was D'Alembert principle, there was Fermat theorem or Fermat's principle, It was Noether theorem. It took me some time before I understood that it was a woman mathematician, who had given us those theorems. I think it was really lucky that she had a very supportive family. And it was also very lucky for us and for mathematics that Hilbert, Klein, Einstein recognized her merit and they mentored her. So I think her story underlies the importance of mentoring by people for women. And apart from Hilbert, who actually told his colleagues that the gender was not relevant, as this was an appointment to a university and not a public bathhouse, there was also Klein, who said, "I'm ashamed to occupy such a preferred position beside Amy, who is so far superior to me." I think it was a great thing that Emmy Noether had these mentors. Her story, as I said, also underlies the importance of a very strong family support. And it is quite interesting that even with the support of doyens like Einstein, Emmy Noether had to be content with a position in a women's college, that's the Bryn Mawr College, away from Princeton, and traveled twice every week to give lectures there. Have things changed much? Yes, to some extent in the mindset, but I think there is a long, long way to go. And it is still not uncommon that it's a good choice for women scientists to do have a career, unless they get a chunk of luck. We will all do well to enhance this part of Emmy Noether's legacy as well. Thank you very much, and sorry for taking a few minutes extra. Thank you.
Well, Professor Rohini, we even didn't look at the time till now. That is how, very typical of your lectures, always very, very inspiring and extremely profound in its content. And today you delivered yet another very inspiring story of Emmy Noether, who is one of the pioneering or greatest mathematicians, and how her work, provided a really underlying framework for a large space of particle physics. And I think the icing on the cake, you also brought up both Higgs boson and neutrino, and and I mean, nobody can do with this kind of bandwidth and precision of how particle physics can be dealt in an hour-long talk. Thank you so much, and it is really wonderful. It's a feast to our eyes and ears.
Thank you, sir.
Large number of questions, and I don't know how many we'll be able to take up, but let me start straight away with one question from Professor Vivek Datar, who is instantly responsible for this
topic. Yes.
And topic particularly. So I think I should give him the honor of taking the first question.
Yes, Vivek.
Okay. Hi, Rohini. Nice talk. Very nice talk.
Thank you.
My question is based on the, you said that there is a problem which Hilbert and Einstein talked about to Emmy Noether. Now, does that have to do with the gravitational wave emission?
No.
That has nothing to do with that.
No. It is just
can
that
you explain
energy
that a little bit more? What was the problem?
No, the whole point is that when you calculate the energy momentum tensor, as you remember, the Einstein equation involves the energy momentum tensor.
Yeah.
And in the energy momentum tensor calculation, you had to include the back reaction of the metric. And that was not included. If you didn't include it, you had a problem. And then Hilbert with his ingenuity understood it and included it, but he didn't know why it had to be included. So it was more a question of inclusion of back reaction in the equations.
Okay. So it's like considering the whole system rather
Exactly.
than...
Exactly. You got it.
Thank you.
And that was the point that Hilbert had appreciated. But in the way she derived this equation, it became absolutely clear, because it was like the counterpart of that second term that I got in my equation. You remember dl by dq dot minus, and it was that right-hand side of that divergence equation that one realized that it had to be there. It was not something that you put in by hand, it had to be there. So right now, I mean, in my article, I spent more time on it, but right now I will not be equipped to answer in more technical details.
No, that's okay. That's
fine. Yeah. But that is essentially the idea.
Ms. Rohini, I will start taking some questions on the YouTube.
Yes.
Uh,
Yes.
One question from Harishankar Tripathi. Does Noether's theorem violates the principle of causality?
Why should he do that? I don't understand. Can you explain your question? Because
no, this is a YouTube question.
I know, but so he can't talk. Okay.
Yes.
No, because I don't see the problem. I mean, I don't see how it implies violation of causality, because changing the origin, as long as we write down all the equations of motion, which are only forward equations of evolution, right? A system from a time t, from one particular impact of time, we give how the system evolves forward. So I don't think that changing the origin of time anywhere means that you change the direction of time. That's the only way I can answer this question.
I hope you got the answer. And there are two questions from Vatsal Trivedi. One actually a kind of a request that can you please repeat the example that you gave for internal symmetry just before you introduced gauze?
Okay. I can do that. Think of, for example, think of an electron falling through a potential difference between two plates. And one plate is at potential V1. Let's say V1, one plate is at potential 10 volts, let's say. And other plate is at 0 potential. Then you would say that the electron gains energy of 10 volts. Now, instead of measuring the 10 volts, okay, 0 was a bad idea. Let's say that one plate is at voltage 10, other plate is at voltage 2. And then we say that the total energy that the electron gains is 8 electron volts, because it fell through a potential difference of 8 volts. But now you say that instead of calling the upper plate to be at 10 volts and the lower plate at 2 volts, I can also say that the upper plate is at potential 8 volts and energy at the lower plate is at 0. And the energy that the electron creates is E times V2 minus V1. So it can be V2 minus V1, or I could define a V2 prime, which is V2 plus V0. And V2 minus V1 will be V2 prime plus V0 minus V1 prime minus V0. And it will be V2 prime minus V1 prime. So no matter what is the origin of my potential that I choose to name my potential, give my potential, the answer will, energy or the Ford's law will remain exactly the same. So this means that there is a transformation in the quantity in the quantity called potential. And this is an invisible quantity. What it means is that you measure only potential differences. You don't measure absolute potentials. Am I making sense?
Yeah. So,
okay.
So again, as I said,
again, it's a YouTube answer, so I don't know.
Yeah.
But this is what I mean.
Yeah, but there also another question from the same participant. What exactly is meant by a function not having explicit time dependence? Can you please give an example?
I mean, for example, if example I can give very easily is, let's go back to this example of pendulum that I was giving. I hope they can still see my screen. So let me go back to that slide. What's the name of this person? Then I can address the person.
He's from CBS.
Okay.
Vatsal Trivedi.
Okay, so Vatsal, look at this here. This is the total energy of the system, right? And here you see, for example, at the point B, the total energy is only potential energy. Here it is potential energy plus kinetic energy. Okay, in between. Then here there is no potential energy and only kinetic energy. And over here there is no kinetic energy, only potential energy. But energy, that is the total energy, sum of potential per kinetic energy, is exactly the same throughout this path. So the pendulum oscillates as time goes on, but the total energy depends completely independent of time. So it does not explicitly depend on time. Does that make sense now? I hope it does.
I hope, yes. Yeah. Thanks. And there was one question from Abhinav Chaudhary.
Hmm.
The theorem describes the conserved quantities that follow invariance under continuous transformations.
Hmm.
Does an analogous theorem of such generality and scope also hold for discrete symmetries?
Yes, but not of such generality, and I don't think a theorem has been proved. But again, I know that there are conserved quantities under discrete transformations, but it gets a bit hairy. So the simple answer is no.
Okay.
The simple answer is no. Such theorem doesn't exist.
Okay.
I'm glad that you noticed the dependence on continuous symmetries. Whosoever asked the question, I want to compliment you. For that.
It's a very regular and you always ask nice questions. So I think
I imagine it's a he, and I'm because you said the
how
name.
the content in fact is more brought out when the right questions are asked to the speakers. Thank you very much for your questions. And so Vatsal Trivedi, to whom you answered, of course, he acknowledged that he understood. And
Okay.
you. And let us move forward. There's a question from Sachin Shukla. Can you explain how we can use the time invariance of proving energy conservation? It feels like Noether theorem is nothing more than the cyclic coordinates concept in
No, you are quite right. I mean, you are actually quite right. So this is exactly what she says even in her paper. At that level, applied to mechanics, it is nothing more. Okay? But the point is that she doesn't prove it only for mechanics. That is the whole point. And that is actually the sense of generalization and the mathematical awe of the whole story. But otherwise, this is cyclic coordinates. You are completely right.
Excellent. So are there any more questions from the Zoom window? Anyone would like to ask? Of course, you can unmute yourself and...
I just had a comment, Satya.
Yeah, please.
Very nice talk, Rohini. I just have pasted the link to your article in Physics News, which is free for download for people who want to.
Oh, thanks, Vandana. Thanks, Vandana.
Because that was also a very nice article, and in fact, that issue had a cover page which depicts Emmy Noether's rings and her equations.
In fact, actually, Vandana, good that you did this, because I forgot in the end, the time was short. I wanted to actually put a cover page of that article in my talk.
I have put it in the chat.
Thanks that you have done it. And I'm glad you did it. Yes, because I was going to do it.
Another point is the similarity which I wanted to tell you. Like other day we were discussing about this in connection with Anandibai Joshi. So here also, if you look at it, Emmy Noether, Lisa Meitner, and also this Agnes Pockel, these all come from the Jew background.
That's
so
right.
Somewhere I think there was this family which put them into education coming
That's
from
right.
that. And of
That's
course,
right.
they all suffered because of it is there. But at least their family was able to support, let them support, give the support so that they could follow their passion.
Vandana, I will actually add here that when I go and look at my Lilavati's daughters, where many people have written stories, you would see that almost, not in all cases, but majority of cases, the family support was absolutely crucial.
True.
So, and I think that is something we all who do science, all women know this, in fact.
Yeah, that's true. That's the point.
Ms. Rohini, there's one more question from Sachin Shukla, which I actually missed in okay, let me read that for you. In the time invariant symmetry for proving energy conservation, we take displacement in time, but the change in coordinates in symmetry is both q prime t and qt, q of t, that is at the same time.
Yeah. Now, the point is that it's there is a difference in the symmetry transformation of the parameter qt and symmetry transformation of time itself. Okay, these are two separate different transformations. I shouldn't have put them, perhaps mix them together, because that gives rise to some confusion. But the point here is that by choosing to the origin of time to be somewhat different, effectively, since you know that the correct solution, that is with respect as a function of time t prime, whatever is the solution of equation of motion, which is q prime, should be the same number as q of t. And that is the equation we have used. So there is an indirect dependency of q on t that has come through that. And it is that independent, that change in the coordinate that we have taken into account for doing the further calculation. I hope I'm clearer. And but right now, I think this is all that I could actually say.
Coming back to Zoom, there is a question from Amol.
Yes, Amol.
Hey, I thought I noticed something, but I may have noticed it wrongly. So you mentioned that Emmy Noether found that the atmosphere in Princeton was not as congenial as the one in Germany. On the other hand, when Einstein writes an obituary, he says that, oh,
no, I noticed it. I have noticed it, but this is...
Do you have any comments on this?
Well, my comment here is that this was Einstein's perception versus Emmy Noether's own perception. Because there is a written evidence, actually, where she says that I do not like Princeton professors. I mean, she went to Princeton twice a week. Of course, she liked Einstein. So the comment is not about Einstein, clearly. But she was not happy about the other members of the fraternity. And she actually goes on record saying this. So I actually noticed when I saw that in the obituary, and I even debated whether I should include it, but I decided that that was his perception, so I should. And the important point that he made is correct, is that her association with her pupils in both in Princeton and in Bryn Mawr was enormously good, and she has actually recorded and made statements about that. So we can leave it at that. But you're right. I mean, you noticed something which is correct.
First, only there's one more question from Zoom. This is Harihara Boy. Are you there? Can you please ask question yourself?
I see the...
Yeah, now I don't see... no. Harihara, please unmute yourself.
Satya, there is also one typed question by Raj.
Yeah.
Yeah, but that's a very difficult question to answer. I mean, that's what 70 years of particle physics, at least one example I can give. How do you identify symmetries of a system?
So
I think I would not want to answer that.
Okay. So that is one question from Raj that you already seen then. Yeah, but Harihara somehow
vanished.
Okay. We can send her a mail.
Okay.
Okay.
Once again, look at YouTube. No, I don't find any more new questions from either. So yes, it is time to thank you, Professor Rohini. And I don't think we can really thank you enough on that. But I hope you are again going to talk a little bit more. Okay, one second. Harihara Boy has come. No, I think he's having difficulty. So to talk on a related topic a little later, of course, we look forward to that lecture as well. But for now, thank you very much on behalf of all the participants for this wonderful lecture. And we all obviously enjoyed a lot and learned a lot, also inspired a lot, I must say. So thank you very much. And so with that, we'd like to close today's session. Thank you all of you, and take care and stay safe.
Thank you very much, Satya. And thank you, everybody. Bye-bye.